Okay, just to make sure everybody knows, I'm not going to be here on Friday. I'll be in Tulsa with the Kaiser kids. And so what will happen is on Thursday, or maybe Wednesday afternoon, I don't know, I'm going to record a lecture and I'll post it on Blackboard. Well, yeah, it'll be through Blackboard, but it's on YouTube. So you'll need to watch that before Monday. Okay? So you're going to have like 3 days to watch it. Okay? So I'll try to remind y'all on Wednesday also. Yeah.
IR is on this test, right?
Yes.
Okay.
So what chapter is this again?
Well,
I don't know.
Is it, I thought it was
I actually don't know the numbers.
12, 14,
12, 14, 15, 16, and the beginning of 17. The basic benzene reaction. What we do today is not on the top. Okay? That's right. Telling ya. Okay, here we go. Can you see them good enough? Should I outline them or? Okay. I have 12. I think there's 13. Thanks. Okay, so what is the first reaction called? That called Friedel-Crafts acylation, okay, and you put carbonyl and whatever the R group is on the ring through an acylinium ion. Okay, then what is the zinc, mercury, and HCl called? The what? Clemmensen what? There's another word with it. Clemmensen reduction. Okay, what does it mean to reduce? Add. And what the Clemmensen and the Wolff-Kishner do is they reduce this carbonyl all the way down to a CH2. So the correct answer is okay. And there's no rearrangement. That's why you do it that way. Because if you wanted to make this and you tried to do it this way, guess what? You wouldn't get that. You would get this one. Okay, because it would rearrange. That would be the major product. You would potentially get a small amount of that, but it wouldn't be the major organic product. Okay? Okay, so we're going to look at the rates of EAS. EAS is short for Electrophilic Aromatic Substitution. Okay. As compared to benzene, an activating group is a group that makes the compound react faster than benzene. And a deactivating group is a group that makes the compound react slower than benzene. Okay, so here's an example of just Z is whatever. There is no element Z. Is an activating group. There is an element Y, however, that is not it. It's just random. All right, so makes it, this is more reactive with Z, it's less reactive than the compound with Y on it. Okay, so here is toluene. Okay, toluene is methyl on a benzene, remember. Toluene reacts 20 to 25 times faster than benzene if you do an electrophilic aromatic substitution. In particular, they use nitration. What are the reagents for nitration, just to have to review? H what? HNO3 and H2SO4, okay. And what do you put on the benzene ring? Oh, what? An NO2, okay. All right, so a methyl group thereby is classified as an activating substituent. Compounds with activating substituents react faster than benzene. Okay, faster than benzene. Okay, if you put a trifluoromethyl group on a benzene instead of a methyl group, that undergoes nitration 40,000 times slower than benzene. Okay, a trifluoromethyl group is a deactivating substituent. Okay, now do you have any idea why toluene, a CH3, would be an activating substituent and CF3 would be a deactivating substituent? Do you have any idea?
Electronegativity.
Okay, electronegativity. So where is the electronegativity? Up here in the fluorine, right? And what does that mean to be electronegative? What do you like? You like electron density, okay? So if you pull electron density out of the ring, that ring is not able to go and attack and electrify because it doesn't have as much electron density in it. Okay, why is a methyl group an activate? Yeah, it pushes electron density into the ring. Do you remember when we talked about carbocations? Primary, secondary. Oops, I added too many hydrogens there. And no, I didn't. I need one. 1, 2, 3. Yeah. And tertiary. So that one's got 3. Okay. Which one of those is more stable? The tertiary. Okay. Because the methyl groups are all donating electron density into the carbocation. So if you push electron density into the benzene ring, that makes it easier for it to react with an electrophile. Because remember, the benzene ring is breaking its aromaticity and pushing electrons towards that electrophile. Okay, so it's the same basic principle as that. Okay, so activating groups push electron density into the ring. Deactivating groups pull electron density away from the ring, out of the ring. Out might be better than from, I don't know. Probably doesn't matter. Are y'all writing there? No. Just give you a whole blank. Oh, I gave you a couple things. Yeah, if you're activating, you're pushing electron density into the ring. If you're deactivating, you're pulling it out of the ring. We're going to keep using those terms, and so that's why we got to get that straight. Okay. All right, so here is toluene. We're going to nitrate it. Notice that the groups are the reagents are HNO3 and H2. Okay. Now, when you put an NO2 on this benzene ring, do you see how many possible products? How many possible? 2? What are the 2? That's not the possibilities. There are 3 possibilities, right? You can get it ortho, meta, or para. You could get all 3. Do you see that over here? This one is repeating this one, and this one is repeating this one. Okay, I just want to make sure. All right, so here's what happened. Here are the three. Okay, well, what they found when they analyzed is that they got 63% of the ortho, 34% of the para, and 3% of the meta. They actually get a little bit of the meta. Okay. A methyl group is considered an ortho-para director. A methyl group is telling the incoming electrophile where it can go. It's saying, I'm on the ring already. I have first dibs. So I'm telling you, you can go ortho and para, but you don't get to go nitro. You don't get to go meta. That poor little nitro group has to go where the methyl tells it. Okay? A group on the ring is going to affect both the rate at which the reaction is going to occur and the ratio of the products. Okay, it's going to affect two things, rate and ratio. Okay? Wow. Okay, here is a T-butyl group. A T-butyl group is also an alkyl group, just like a methyl. It is also a activating group, and it is a OP directing group. So the T-butyl group is saying, you can come in here, you can go ortho or para. Guess what happens with this one? You only get para. Okay, so much for writing. Didn't want to happen there. You only get para. Why? What do you think that is? It's bulky. It's blocking these sites, okay, because of its size. Okay, so the group that comes in only goes to the para position. So it's important to also look at the size of the group. Okay. When you did lab, you did benzene plus T-butyl chloride and AlCl3, and you put a T-butyl group on the benzene. Well, once you make this, it's more reactive than the benzene, and so it reacts a second time. And it's very difficult to make T-butyl benzene because of that. Okay, you would actually make it, you try to make it a different. Okay, because this is more, if your product is more reactive than where you're starting, okay, as soon as you make the product, it reacts, okay? So typically we make products that are not more reactive than the starting material, and so we don't have that in those reagents and conditions. So we don't have that problem, but with this one y'all did, that's why you got di-T-butylbenzene, and you got the para one because of the steric hindrance, which is really nice because in that last one I showed you with the toluene, you would have had to separate them, okay, the ortho and the para, depending on which one you wanted. So it can be very difficult to separate them. Oh, that's probably why. Okay, so alkyl groups are activating groups and they're OP directors. Now, if you have halogens on there, that changes it. So like that CF3, that is not considered a regular alkyl group because it has a halogen. Okay. So don't get that mixed up. And speaking of CF3, okay, here's CF3. We're going to add HNO3 and H2SO4. Okay. Now here are our three possibilities. Okay, ortho, meta, and para, and look what happens. The meta one is for 91% of the time. The ortho and para are really low. So if you are a deactivator, you can typically be a meta director. Okay, there are only two classes of directors, meta and ortho para. There isn't such a thing as an ortho-meta director, okay? Not in electrophilic aromatic substitution, okay? Electrophilic aromatic substitution is only two kinds. And you're either going to be an activating group or a deactivating group as well. Okay. Here I have all of the ring positions are deactivated, but the amount of deactivation is greatest at the ortho and para position. So I'm going to show you that. Okay. Are you writing that down or? Okay. I'm not sure if I have a blank next or not. Yeah, I do. Okay. So I can check. I was hoping I did. Okay. So here is our benzene. And I'm going to put on it the CF3. Okay, so all I'm going to do is do the part where the electrophile adds to the benzene. Okay, so there's my electrophile, NO2 plus. Okay, and I'm going to add it to the benzene ring. So I'm going to take my benzene ring and I'm going to go to the N, and then you go out to the O. Remember? Okay, so what do I have now? Since I use that double bond, I'm going to put that H on there so that y'all don't forget about it. Okay, so here I'm going to have, okay, here's what I didn't change. All I did was one arrow. Okay, there's my H. All right, so now I'm going to have my nitro group on the benzene ring, right? I'm just going to write NO2. You can write out the loose structure if you want. Okay, so what else am I missing on that? A what? A plus. Here's my plus. Okay, it's positive. It's a benzononium ion. Okay, that's ortho. Notice where the plus is. It's next to a group that is electron withdrawing, not electron donating. So what does that do to that benzononium ion? It makes it more stable or less stable? Makes it what? Less stable, okay? All right, so now look at, and that's less stable than it would be in benzene. Okay, so now we're going to go to the meta spot. So I'm just going to use this double bond. Let's do the green group. So I'm going to go there. I'm going to go out to there. Okay, so what do I get? Here is my intermediate. This is what we didn't change. Okay, now I have an H here. An H here. Okay, so I'll put my H here and here. And if we're talking about the meta spot, it's going to be NO2 here. And now who's positive? Which carbon is positive? The one what? On the bottom, the one that's para. That one's positive. Okay, so is that destabilized by the CF3? Well, let's look at the resonance forms. Can I get it to end up there? So what happens if I do that? Where does the plus end up? I maybe should have. There's a lot of stuff to draw on your ring that didn't change. Okay, so if I put that double bond down here, on the bottom left, I've got a double bond, and this carbon is now positive. What if I do another resonance form and go like that? Notice what doesn't change. I'm going to draw what doesn't change. That's an F. It doesn't look like one. Okay, and now that double bond is over on the left side. And where's the plus? It's over here. So did the plus ever end up on the carbon the CF3 is on? Did it? Okay. What about the para spot? What if we do the para one? So we're going to add. apparently we need the purple root because we haven't had that yet. All right, so we're going to go down to the N, now to the O. Okay. I'm going to draw what I didn't touch. I didn't touch the double bond. I didn't touch that double bond. I didn't touch the CF3. It's still attached. Okay, so if I'm putting, let me put those two hydrogens on there. The NO2 in the para spot. Okay, now where is my carbocation? It's over here on the meta spot. Well, that's not on the carbon next to the CF3, is it? What happens if you do resonance, though? Where does the carbocation end up? Because remember that overall, the molecule is all those resonance forms added together. Okay, I will get this part written in, and then I'll move out of the way. Draw what didn't change. Okay, so if I take those electrons and put them to the right, I'm going to have a double bond. And where's the plus? It's right here. Okay? CF3 is pulling electron density out of the ring. It is less reactive than benzene. Okay? But which ones are worse? Well, the ortho and the para are worse resonance forms than the meta ones. So the meta, it'll still react, but it'll go to the meta spot because that is the best of the worst. Okay, they're still not great. We're going to look at Toluene in a second. Okay, so it's like going to the polls and voting. You have to pick the best of two. Don't you feel that way? Have you ever, I mean, let me tell you, I've been voting for a while now. I'm like, every time I go, I don't know who to vote for. I don't like anybody. Why can't we have intelligence run for president?
President.
No, are you kidding me? I don't want that job. I'd probably die. I'd probably have a heart attack. Yeah. That's probably why all the intelligent people are smart to say.
I've seen the presidents before and after their terms.
Yes.
They're completely great.
Yeah, and they totally age. Mm-hmm. They probably age 10 years in 4 years. Yeah, it's like, oh my God. Okay, so the best of the worst. The best of these resonance forms are going to be the meta attack, where the group goes meta, because the plus does not end up on the carbon with the CF3. Now, if you look at toluene, where we have a CH3, okay, and we don't have any of those electronegative halogens on there, heaven forbid, right? Okay, look what happens when we add our nitro group. We'll add it, or, oops. This is what happens. I was trying to work ahead. Okay, so we're going to do just what we did on the last slide, but we're going to have a methyl there instead of a trifluoromethyl. Okay, so we're going to go from here to here and out to there. So what do we get now? We have a, all right, I'm drawing what didn't change. That's a CF3. Looks kind of crazy. Okay, so now my nitro is attached to the ortho, and look at what carbon has the plus. The same one that we had with CF3. What am I? What? Oh, my bad. I was still in that mode, wasn't I? All right, hang on, I'll fix it. That's okay. I can fix that. I wrote that other thing screwy anyway. Okay. That'll give you time to catch up to me, right? I planned that. Yeah. Okay, now look at that carbocation. It's tertiary. Okay, the CF3 is donating electron density. Okay, that's ortho. All right, what about when we do meta? I'll draw those on there. Okay, we're not going to touch this one. So this time we're going to touch this double bond. That's going to get us to this one. And by doing this over and over and over, y'all will get it right, right? That's the idea. All right, so this carbon down here is going to be positive. Okay, notice that if you draw resonance forms for it, you cannot get the plus up on the methyl on this carbon. You can't get it there. The plus is going to end up here, and then it's going to end up here. Okay, so it doesn't get any extra stabilization from the methyl. Here, I'll draw one of them, because we got some other stuff to do. Okay, so this is how I should have done it on the other screen. This is our double bond, this is our plus. Okay, so if you move this over and do the next one, the plus is going to end up there. Okay, that making sense? So you see that the methyl never really gets to help very much. It helps a little because it's still donating electron density to the ring, but the ortho, it super helps. What do you think happens with the para? Okay, so let's put it on the para spot now. Now, this is the purple route, which is always the best route. You know, I don't know about that. Okay, so I'm going to put my nitro on here in the para spot. Which carbon is now plus? This one is, right? Okay. Well, it's not right next to the methyl, but what happens if you look at the resonance form? Look at what carbon is going to end up plus in that resonance form. Okay, I'm going to draw what we didn't change. Hopefully. Okay, so now that moves down there. Where's the double bond? It's the vertical over here. And who's now positive? This carbon's positive. So you see that the methyl group gets to directly help stabilize that benzene. So ortho, and that's why ortho and para are always together. Okay, and meta is its own thing. Okay, well, these are going to be more stable than these benzenonium ions. So because of that, we go there. Okay, strongly activating groups are groups that donate electron density into the ring a lot. Okay, so look at this. Notice that that O has on it what? Lone pairs. How many? 2. Okay, so you can draw resonance forms for this. Okay, what is that going to look like? Here, I'll write it in black and then I'll write what changed in purple. I'm going to put that H there. Okay, so if you look at a resonance form for this, because you have a lone pair right there, what do you get between the O and the carbon of the benzene ring? A double bond, and I thought it was on purple. A double bond, and the O is positive. Are you positive? Good. Okay, is that, what else? What did we do over here? We put something on this carbon. What did we put on it? a lone pair. Okay, so this carbon is negative. So if you are, because we're putting the electrons out there, we haven't added the electrophile. Okay, so if you're going to reach out and grab an electrophile, your high electron density spots are going to do it. That's going to be the ortho and the para spots. Okay, and since when we had a methyl group, we were donating electron density into the ring, but it was not through resonance. Remember, resonance is a stronger effect than through the bonds. What is that called? Hyperconjugation and induction. Okay. Hi. Okay, so get rid of that. So here are our ortho and para. Notice that they add up to 100%. We didn't even get any meta. The other ones we got a little bit, but here we didn't even get any. Okay. Phenols nitrate 1,000 times faster than benzene. Toluene was how much faster? Did you write that down? 20 to 25. You don't have to know that number, but I want you to see the difference because this is a resonance of. Okay, what do I got down here? It really did, didn't it? All right, we got it on there. Okay, this is anisole. Anisole, you'll see, also has 2 lone pairs on the oxygen attached to the benzene ring. Okay, and when they put a halogen on there, it reacts without using the Fe. You don't even have to have the Lewis acid catalyst. That's how good the oxygens are. Okay. And they got 90% yield of the para. I would not expect you to know that. What I would expect you to do is put ortho and para. Okay? Because, I don't know, this isn't very big, so you wouldn't think that that would have hindered the ortho spot that much. Not sure why it's fair, because I don't think the methyl's very big. OT-butyl, sure. Okay. So the methoxy activates the ring so much that a Lewis acid catalyst is not even needed. Okay. It's still the same mechanism. Grab the Br and the bromine leaves, and just like before. Okay. Now these groups are deactivating groups. Okay. What is different about them from those 2 activating groups that were on the left hand, the last slide? And notice what we've got here. We still have lone pairs on the O, but is the O directly attached to the benzene ring? No, you got that carbonyl. Okay, the same thing for a nitro, which unfortunately I don't have drawn out, so I will draw it out. Okay. So here we have nitrobenzene, NO minus, and double bond O, and the N has that plus on it. So what do you think that's going to want to do to electron density? Pull it. She's going to pull it. Okay. You can even draw resonance forms for these that show the electron density going out of the ring. So if I do that for this one, notice where we go. Out to the O. Just like when we did nucleophiles attacking carbonyls. We went to the carbon of the carbonyl, go out to the. This would be the same thing. You go up to the N and you go out to the O. Okay, so that's going to put what here? A plus. Okay, so it's pulling electron density out of the ring. Okay, so if we add HNO3 and H2SO4 to this, first of all, what does HNO3 and H2SO4 put on the ring? NO2, good. Notice that it goes meta. Okay, If you do bromine and Fe, what does that put on the ring? Br2 and Fe, what are we going to put on our benzene ring? Not Fe. Okay, we get the meta. Okay, deactivating groups, deactivating meta directors destabilize attack at ortho and para positions more than at meta positions. It's still deactivating. It's still going to react slower than benzene. But the better spot to go to, the best of the worst, is meta. Okay? The best of the worst is meta with these guys. Okay, so here's your halogens. What do you think about that? Well, what have we got a lot of on that chlorine? We got a lot of lone pairs, right? But chlorine is known for its electronegativity, right? Okay, so what happens when you do a reaction with, there we go, that's what I want. When you do this reaction, HNO3 and H2SO4, what are we putting on the ring? Go, girls. Okay, here are your three possibilities. Guess who wins? Ortho and para win, but chlorine is withdrawing electron density. The halogens are the ones that are kind of in the middle. Okay, they're the ones that wreak havoc with your brain. Okay, so the rate of nitration of chlorobenzene is about 30 times slower than benzene. Okay, but the halogens are deactivating due to their electronegativity and ortho-para directors because of their pairs. Okay, so I'm waiting. Okay, because I'm going to draw out those things again. Like I did on the other one. I have no idea if I have a blank page next. Sometimes it's just not what I want it to be. Okay, so we're going to add our nitro group. Okay, and we're going to add it ortho. And then we're going to add it meta. And then we're going to add a para, just like we did before. I'm being consistent. But this is true, remember, for every one of the electrophilic aromatic substitution. Okay, so here is path A. We're going to do them in order, ortho, meta, para. All right, so we did that. Okay, can you draw what you have after that step? Okay, remember to draw what didn't change. Wow, it's like not wanting to make circles now. Okay, you get that? Are you getting tough at that? Should be really tough at that. Okay, now what are we going to do? We're going to draw resonance forms. Now, you can draw the resonance forms where the double bond moves around the ring. But there's an extra one for this, where the chlorine donates an electron pair to the plus. And so because that gets stabilized, that's why chlorine is, okay, so I'm going to draw what didn't change. Okay, and so here I'm going to put a double bond to the chlorine, and the chlorine is going to get the plus. See that? So the chlorine is, where have we seen chlorine have a plus charge before? We saw it. Way back in the dark ages. Okay, do you remember, I'll have to erase it because I won't have a room, doing this on double bonds? And what did we make for that was an intermediate? Good review for the final. What is that? Remember a chloronium ion? You got chloronium ions and bromonium ions. Okay? They're chlorines and bromines that have plus charges on them. You get them because they're big elements and they can help stabilize extra stuff with those long. All right, now I'm going to have to erase that. So if you want to write that down, it won't be on your slide. So write that down. Let's see if I can get to the eraser. If you forgot all about those. Okay, and remember, the chloride ion comes in from the bottom. That's why they're anti. Okay, so now look at the meta. So here, we're going to go from here to here. Okay, and we're going to do the meta one. So that's going to look like Are you throwing stuff around over there? Okay, what does this carbon get? Okay, so do you see that if you do resonance forms for this, okay, where does the plus end up? Here, and then that one can move over and the plus is going to end up there, okay? So notice the chlorine doesn't get to help, okay? But when you add to the para spot, look what will happen. Maybe I won't have a lot of room to write my lone pairs in, y'all. Okay, so who's positive now? Which carbon? This one is. Okay. If you do resonance, look what's going to happen. Where's the plus going to end up? It's going to end up here, and then the chlorine is going to get to go to the party and donate its little lone pairs. Okay, so it would be like this. I bet a lot of these might be in your book. If I said for sure they were, they wouldn't be, so I'm going to say might be. Gosh, this thing is lagging. Okay, there's my chlorine. Okay, and now over here is my double bond, and this carbon is plus. So now we can do this. Okay, is that making sense? Which is the same as that one, except the nitro's in the para position. Okay, so when you have the O groups, like the OH and the OR, okay, those things are going to also do this exact same thing. So we'll draw one of those out since we didn't do it earlier. So if you have and let's just go for the good old nitro. What is that electrophile called? Let's see if you remember that. What is that called? Nitronium ion. Nitronium ion. Okay. All right. So looky here. We're going to the N. We're going out to the O. And you know it doesn't matter which O you picked, right? the thing is linear. Okay, so if I draw out one of the things, I'm not going to draw all of them this time. Okay, so over here, I'm going to have my NO2. And where's my plus? It's right here, right? And look what happens. That little O is donating its lone pair down there, do a little resonance action. I'll get out of the way. Okay, so that O now is double bonded here and is positive. Okay, and there's still one lone pair on there. Okie dokie. So are you seeing the different ways? Okay, it doesn't matter what the electrophile is. You could just write E plus for all of them. Okay, and it all works the same for every one of. That's why we did all the reactions first. Okay. Now here are the classes. Okay, it's like I put it all together. So very strongly activating groups are ortho para directors. These are your N's and your O's. Okay, notice what they have. They have lone pairs on the atom that is directly attached to the benzene ring. Okay? These are also strongly activated. Okay, so did you get that this is where the benzene ring's attached? Where the little hyphen is? Okay, just sure. Okay. Your book put the OR in strongly instead of very strongly. There really is hardly any difference between those two categories. Okay, if you look down here at this one, do you remember what the O in parentheses means? Yeah. Okay. It means there's a carbonyl. Okay, so there's your lone pairs. That's your clue that they're OP directors. Every single atom that has lone pairs on it that is directly attached to the benzene ring is an OP director. Remember, the guy on the ring gets to tell the new guy where he can move in. Okay, he was there first. So he tells the new group where to go. Okay, these are regular activating groups. R groups, double bonds. What's AR?
Argon.
No. Dang, no. It means an arrow group, which is another benzene ring. Another benzene ring. So AR is a, so you could have a benzene ring attached to a benzene ring. Okay? All right, yeah, that opens a whole new ball of wax, doesn't it? All right, so here is H. H is no substituent. Okay, that's just plain benzene. All right, now here is the last one. This has deactivating the halogens. These are OP directors. Notice that having one halogen, it's still an OP director. Okay, but when you get to the other ones that have more than one, like CF3, those are strongly deactivating. Those are the meta. Notice that this one right here, okay, where it's attached to the benzene ring, y'all, is a carbonyl. And then, okay, it's important to see the two sides of the ester. Okay, all right, because we're going to use them next class, which will be Friday. Wednesday we'll review for the test. Okay, Wednesday we'll review for the test.